Hello everyone. Today in this lecture we are going to see some of the fuel air cycles on which the internal combustion engines they operate. There is a reason why these cycles are called as fuel air cycle. Okay. The reason is that in any internal combustion engine, fuel and air they are combined and combustion takes place. Combustible material is fuel, and for anything to burn, for combustion to take place, oxygen is required, and this oxygen is available freely from the atmospheric air. Hence, these cycles they are called as fuel air cycles. Now, for their analysis, there has to be some or the other assumptions. Let us see what these assumptions are when you want to analyze a fuel air cycle. First, assuming the working fluid to be only air. The reason behind this assumption is that there are a number of different fuels that are currently being used or were being used in an IC engine. Now, for every different fuel, you cannot have a separate analysis. It will be a very tedious and a tiring task. Hence, to simplify the matter, only air was considered to be the working fluid. Constant specific heat of the working fluid. This is an important property. The specific heat of the working fluid is going to be constant. Specific heat is the amount of heat that is contained in a unit mass of the substance. Okay. Then, prior to combustion, there is no chemical change in either fuel or air. That is, before combustion takes place, there is not going to be any change whatsoever in the chemical nature of either air or fuel. Whatever bonds are present in the fuel, those chemical bonds they are going to remain as it is, and whatever is the chemical composition of the air, that chemical composition will remain as it is without any change prior to combustion. Of course, when combustion takes place, for that these chemical properties they might change. Some bonds will be broken, some new bonds will be formed. Then, subsequent to combustion, the change is always in chemical equilibrium. This is very important. The equilibrium, whatever is the change in combustion, whatever is the change, this change is going to remain in equilibrium. Like, for example, if you consider a molecule of methane, that is CH4, if you want to burn it, you have to form the chemical equation wherein oxidation of methane takes place. CH4 plus O2. If the combustion is complete, this will give you CO2 and H2O. And this to balance, it will be CH4 plus 2O2. So it will give you CO2 plus 2H2O. So this is called as chemical equilibrium. The equation will be balanced, hence we can say that it is in chemical equilibrium. The processes are adiabatic, that is, there is no exchange of heat between the gases and cylinder walls in any process. Okay, so whatever heat is generated, that heat is completely converted into the pressure which pushes the piston in a downward direction. There is no heat transfer whatsoever between the gases that are formed after combustion and the cylinder walls. Also, the expansion and compression process are considered to be frictionless. The velocities are negligibly small in case of reciprocating engine. If the velocities are taken for what they are in real time in an engine, then it will be very difficult to analyze it because it happens in a fraction, let us say in a thousandth fraction of a second to say the least. Then, in case of constant volume fuel air cycle, following assumptions are made. What are those? The fuel is completely vaporized and perfectly mixed with air, and burning takes place instantaneously at TDC, that is at constant volume. Okay. The first assumption is significant because in constant volume fuel air cycle, before combustion takes place, the mixture of fuel and air is formed, and it is required to be assumed that whatever fuel we are going to use, it is completely vaporized and it is perfectly mixed with air. That is, a homogeneous mixture of air and fuel is present which in other words we can also call as a charge. The first cycle that we are going to see is the Otto cycle. Now, generally, there are two diagrams on which a fuel air cycle is observed, and that is pressure, volume, and temperature entropy. Now, Otto cycle, in other words, is also called as a constant volume cycle, and it is an ideal cycle on which SI engines they are working. Okay, so let us see what happens in an Otto cycle. This is the volume on x-axis and pressure on y-axis. This volume at this point is going to be 0, and this indicates the cylinder head. Okay, but this point it indicates that the piston has come up only until this point, that is denoted by top dead center. So this is the volume that is enclosed at top dead center. This is the volume that has been covered when the piston is at bottom dead center. Okay, this volume which has been left between the cylinder head and the top of the piston is called as the clearance volume. Okay, so let us see what are the different processes with to which an Otto cycle is made up of. The first one is 1 to 2. What is happening in 1 to 2? Let us observe axis by axis. On x-axis, if we move from point 1 to 2, we find that the volume is being reduced. If we move on y-axis, we find that pressure it has been increased a little bit. Okay, so pressure it has been increased. If we come over here on x-axis, the process is isentropic. Okay, on y-axis, we find that there is a slight increase in temperature. So this is an isentropic adiabatic compression of the air as the piston moves from bottom dead center to the top dead center. Piston is moving from BDC towards TDC since the volume is getting reduced and pressure is increasing. This process is called as compression, and since it is happening at a constant entropy, it is called as an isentropic compression. Okay, fine. Now let us go further. Let us observe what is happening in the process 2 to 3. Okay, what is happening in process 2 to 3? Again, let us observe axis y axis. On x axis, it is a perpendicular line which indicates that no change in the variable of x axis, that is the volume, it is going to remain constant. On y-axis, we find that there is a significant rise in pressure as we go from point 2 to point 3. So this is a rise in pressure. And what is happening in TS diagram? Entropy is increasing as well as there is a significant rise in temperature. Why temperature rises? Because heat is added. So the reason for temperature increase is the addition of heat. So as far as the TS diagram is concerned, we can say that this is heat addition, and as far as the PV diagram is concerned, we can say that heat addition is taking place at constant volume. Okay, so this is a constant volume heat transfer to the working gas from an external source while the piston is at top dead center. This process is intended to represent the ignition of the fuel air mixture and the subsequent rapid burning. So in this process, when the piston is at TDC, the temperature increases, which indicates that heat is added, and heat is added in an ice engine when the fuel burns. So we can say that this process is representative of the combustion of fuel while the piston is stationary at the top dead center. Okay, let us go on further. What happens in process 3 to 4? The volume it is increasing. At the same time, there is a significant drop in pressure as well as a drop in temperature at constant entropy. So increase in volume, reduction in pressure indicates expansion process. Okay. So it is an adiabatic isentropic expansion, alternatively called as a power stroke. The fourth process is 4 to 1. Constant volume, since the line is perpendicular to the x-axis of volume, slight drop in pressure, and a drop in temperature. Temperature drop takes place because heat is rejected. So 4 to 1 is going to be constant volume heat rejection process. This process completes the cycle by a constant volume process in which heat is rejected from the air while the piston is at the bottom dead center. So this is Otto cycle. Let us go on further. Next cycle is the diesel cycle. It is a cycle which is an ideal cycle for a compression ignition engine. Let us see what happens. Again, we have pressure and volume, and we have temperature and entropy over here. Fine. So in process 1 to 2, we can see that volume is reducing while pressure is increasing, and this happens at a constant entropy. So this is an isentropic compression process. When the piston moves from BDC to TDC, air is compressed isentropically inside the cylinder, and pressure of air increases from P1 to P2. Now, a marked difference between Otto and diesel cycle is the process 2 to 3. In Otto cycle, this process 2 to 3, it took place at constant volume, but in case of a diesel cycle, this process 2 to 3, it takes place at constant pressure. Since this line of process 2 to 3 is perpendicular to the axis of pressure, this indicates there is no change in pressure. At the same time, as we move from this point to this point, we see that there is a significant rise in temperature, which again indicates that heat has been added during this process. So in case of a diesel cycle, the process of heat addition, it takes place at constant pressure. It is a reversible constant pressure heat addition process wherein heat is added at constant pressure from external source and volume increases from V2 to V3. Next process is 3 to 4. We observe that the volume it has reduced, volume it has increased while the pressure it has reduced. So reduction in pressure and increase in volume, it indicates that it is an expansion process which is happening at a constant entropy. So it is a constant entropy or isentropic process where compressed and heated air is expanded isentropically inside the cylinder and the piston is forced from TDC to BDC, and the pressure it decreases from P3 to P4. The last process is 4 to 1 when the volume remains constant and there is a small drop in pressure, and at the same time there is a reduction in temperature. So the temperature again we know it reduces when there is rejection of heat or where heat is extracted. So we can say that 4 to 1 is a constant volume cooling process where heat is rejected and the pressure decreases from P4 to P1. Let us go on further and see what the next cycle is. Next cycle is Atkinson cycle. What happens in Atkinson cycle? Process 1 to 2. An ideal cycle will consist of 1 to 2 isentropic reversible adiabatic compression. Why compression? Because volume it is reducing whereas the pressure it increases. 2 to 3 constant volume. As you can see over here, heat is added at constant volume over here. So isochoric heating. Then 3 to 4, it is constant pressure, that is isobaric, since the line is perpendicular to the axis of pressure. So the heat is added at constant volume as well as at constant pressure. The next is 4 to 5, isentropic expansion, since the volume is increasing and the pressure is reducing. Next, we can see 5 to 6. As we can see over here, heat is rejected. So in 5 to 6, heat is rejected at constant volume, hence it is isochoric cooling. Then 6 to 1, heat is rejected at constant pressure, hence it will be isobaric cooling. So these are the different processes which take place in an Atkinson cycle. Okay, then let us see what happens in Stirling cycle. 1 to 2, isothermal expansion. The expansion space is heated externally and the gas undergoes near isothermal expansion. 2 to 1 is constant volume heat removal process. The gas is passed to the regenerator when the cooling takes place and heat is transferred or used in next cycle. Then 2 to 3 or process number 3, isothermal compression. The volume it reduces whereas the pressure it is increasing. The compression space is intercooled, so the gas undergoes near isothermal compression. And process number 4, constant volume heat addition, wherein the compressed air flows back through the regenerator and picks up heat on the way to the heated expansion space. Let's go to the next cycle. Brayton cycle. It is ideal cycle for a gas turbine. Okay, so this is gas turbine. Fresh air comes in, compression takes place in the compressor. This compressed air is supplied to the combustion chamber where it mixes with the fuel and combustion takes place. Whatever gases are given out, they are made to impinge through nozzles on the turbine blades. Turbine rotates and useful work is taken out from the turbine shaft, and whatever gases they have expanded, they are given out as exhaust gases. So 1 to 2, what happens in 1 to 2? The pressure it increases and the volume it reduces at isentropic process. Ambient air is drawn into the compressor where it is pressurized. What happens in 2 to 3? Constant pressure and temperature increases, which shows that heat has been added. So compressed air then runs through a combustion chamber where fuel is burnt, heating that air at a constant pressure since the chamber is open to flow in and out. Okay. Next process is 3 to 4, wherein you can see pressure has dropped significantly, whereas the volume has increased at constant entropy. So this will be isentropic process, where heated pressurized air gives up its energy expanding through a turbine or a series of turbines. There might be a series of turbines over here. Some of the work extracted by the turbine is used to drive the compressor, rest is taken out as the useful work. The last process is 4 to 1, where isobaric heat rejection takes place, where the exhaust gases are given out into the atmosphere. So this is Brayton cycle. Now, all these cycles, if we have observed, have been written as ideal cycle. If these are ideal, then what is real? This is the most pertinent question that comes to our mind after studying these cycles. Okay, the four strokes that take place in a cycle, be it ideal, be it actual, real, or whatever, they are suction, compression, expansion, and exhaust. Now let us see, are these strokes represented on the cycle? First, 1 to 2. What is happening in 1 to 2? Volume is reduced whereas pressure is increased. But we know during suction, the volume is increased because piston moves from top dead center towards bottom dead center. So suction is not represented over here. Okay. Then second process, 2 to 3. At constant volume, compression takes place. So this 2 to 3 is not this compression. Okay, because this compression does not take place at constant volume. This compression takes place when the piston moves from bottom dead center towards the top dead center. Okay, so the 1 to 2, it does not represent suction, but it represents compression. And the next 2 to 3, this 2 to 3, it represents combustion, okay, which happens instantaneously. So 2 to 3 represents combustion. The next is expansion. What happens in expansion? The volume is going to increase, pressure is going to decrease. So is expansion represented? Let us see. When we move from process 3 to process 4, we find that volume it has increased, whereas pressure it has decreased. So yes, we can say that 3 to 4 has represented expansion. Now let us go for the next process, 4 to 1. It is constant volume process. Okay, but is it representing exhaust stroke? No, it is not, because we know that during exhaust stroke, piston moves from bottom bed towards top bed. So the volume should reduce and pressure should increase slightly, but this is not happening in 4 to 1. So these suction and exhaust, they are not adequately represented by this cycle over here. Only compression and expansion are represented through processes 1 to 2 and 3 to 4. So this cycle, it cannot be an ideal cycle. So what is this cannot be a real cycle? Sorry, this is only an ideal cycle. So then what is a real cycle? Okay, now this point, it should be point 0. Now let us see if all the processes are represented. Okay, this green line, okay, shown by the green arrow over here. What is happening? Piston is at TDC over here. Okay, it is going from TDC towards, what is this point? This is bottom dead center. So at constant pressure, pressure is not increasing, pressure is not decreasing inside the combustion chamber significantly. Okay, so this 0 to 1, it represents the suction stroke. 0 to 1, it represents the suction stroke over here, because volume it has increased and pressure it increases by a very slight amount, which is negligible. Okay, so this is the suction stroke. Then we have compression, then we have combustion, then we have expansion, then heat rejection, and finally we have exhaust, where piston will move from bottom dead towards the top dead center, thereby driving out the exhaust gases through the exhaust valve. So this cycle, it represents a real or an actual cycle, yet there are some serious flaws in this representation of a real cycle, and they are that these sudden corners or sudden changes in processes cannot take place when the cycle is operating actually. There has to be a smooth transition between these points, and this can be represented like this. This is the intake stroke or the suction. So you can find that the pressure it increases slightly. The pressure is going to increase slightly over here. Inlet valve will open, as you can see over here. Intake will take place and inlet valve will finally close at BDC. Okay, then compression will take place. This process is compression. Then start of ignition or start of combustion, and this will represent the process of combustion. Then this will be the power stroke, and from over here, when exhaust valve opens, the exhaust gases will be driven out through this exhaust stroke. So we have seen this ideal cycle, which does not adequately represent all these four strokes, but these four strokes, they are adequately represented over here. However, this does not represent the actual or real cycle. Why? Because sudden change in the process is not possible. These sharp corners are absolutely impossible to take place when the cycle is happening in reality, in actual practice. So in actual practice, these sharp corners are eliminated and the curves are smooth, wherein we can see intake or suction, compression, combustion, expansion of power, and exhaust stroke. They are adequately represented with respect to top dead center, bottom dead center, as well as opening and closing of inlet valve and exhaust valve. So this is what we call fuel air cycle analysis. Thank you very much.